Hello and welcome to Group 39's presentation video on Project 3. In this project, we've implemented a reinforcement learning system using the Sarsa learning algorithm. The algorithm has been trained to solve what we in this video will refer to as the Acrobat Problem, a simulated world designed to approximate an acrobat hanging on to a horizontal bar using their hands. We'll begin by taking a closer look at this Acrobat problem. The Acrobat world consists of two rigid line segments, which can be thought of as rods. As you can see, the upper rod is attached to a pivot point at its upper end and can rotate freely around this point. The lower and upper rods are connected tip to tip in another pivot point and allows movement and rotation of the lower rod. At any given time, the actor has three possible actions. It can apply a rightward or leftward force at the lower pivot, or it can choose to do nothing, letting gravity do its job. This would be the result of a rightward force. The actor's goal is then to apply forces to the pivot point in such a way that the tip of the lower rod reaches a certain height above the upper pivot point, indicated by a dotted line. In our case, this height is equal to the length of the lower rod. To teach the agent how to solve the Acrobat problem, a reinforcement learning system was used based on the Sarsa learning algorithm. The main learning algorithm is housed in the RL box and simulates multiple episodes of the actor playing the game. In broad terms, this is done by first requesting an action from the policy housed in the critic. This action is then performed in the simulation world, which then returns the resulting state and the reward for doing that action. Using the reward, new values for the policy are calculated and stored. After the episode ends, either by the agent winning or running out of time, all the stored new values are used to update the policy. In our implementation, the policy is a neural network, so updates are applied by running backpropagation with the new values as target values. The main difference between the techniques used in this project compared to the two former projects is the usage of coarse coding for the state representation. In the two prior projects, more primitive one-hot encoded state representations were used. Additionally, the policy in this system uses a neural network as a function approximator, just like in the second project, while the first project focused more on table-based actors and critics. Due to the problem space for the Acrobat problem being continuous, searching through game states, like in Project 2, would be completely unfeasible. In our system, each time an action is performed, the simulation environment returns a new state representation. To represent the Acrobat problem's continuous state in a discrete manner, coarse coding is used. Let's look at an example by coarse coding this point in 2D space. We can overlay a tiling and represent the point's position by indicating which tile it is in, but this isn't very accurate. To overcome this, we can overlay multiple tilings, offset from each other. Now the point's position is indicated by the combination of which tiles it is in each tile set. This information can then be one-hot encoded before being fed through the neural network. This way, we can represent the point's position with high accuracy using a low amount of data. Now in the Acrobat problem, suppose this point's x-coordinate represents the angle of the upper rod, and the point's y-coordinate represents the angle of the lower rod. This way, we can coarse code the positions of the rods using offset tilings. In broad terms, this is how we represented the game state in the RL system in our implementation. To finish off, let's look at the results from training our agent. First, we will look at an untrained agent. Be aware that the agent chooses an action every fourth step on the step counter. As you can see, it's not very intelligent and just makes seemingly random moves. On the right, we can see the learning progression represented as the number of actions needed for the agent to win each training episode. Now we will look at some runs after training. As you can see, it performs much better, and after 100 training episodes, it's able to reach the goal height quite consistently after around 300 steps, or 75 control steps. This concludes the presentation. Thank you for watching.